You know, it's constantly buzzing in the back of my mind. Keeping things powered up.
Hmm.
Whether it's my phone making it through a busy day or, imagining a future where electric vehicles make gas stations a distant memory, it all comes down to better ways to store energy.
Right.
And if you're anything like me, you've probably wondered, what's the next big thing in battery technology?
That's exactly the exciting territory we're exploring today. We're taking a deep dive into advanced materials based on fluorine, drawing out the key insights from a comprehensive scientific text.
Okay.
Think of it as getting the essential knowledge about a really cutting-edge area of energy tech without having to wade through all the dense details yourself.
Precisely. And this isn't just about one type of battery, right? Our source covers a whole range of materials and how they might be used.
A really wide scope, yeah.
But don't worry, we're not going to overwhelm you. Our mission for this deep dive is to uncover the most important ways that these compounds containing fluorine are being engineered to create energy storage that's, well, more efficient, safer, and lasts longer.
Sounds good.
Okay, let's unpack this.
Yeah.
And where better to start than with something fundamental to how our current batteries work? The electrolyte.
Absolutely. In the lithium-ion batteries that power so much of our lives, the electrolyte acts as this crucial pathway.
Right.
It's the liquid that allows the energy-carrying particles, the lithium ions, to travel back and forth between the battery's two main parts, the anode and the cathode.
Okay.
However, the non-aqueous electrolytes we currently use aren't, let's say, ideal. They can struggle to work well with different electrode materials and have limitations in terms of their electrochemical stability.
Right, so it's like trying to get peak performance from a sports car on a road that isn't perfectly smooth.
Exactly.
But our source points to some smart solutions,
Yeah.
like adding a compound called lithium tetrafluoroxyaldophosphate, or LiFOP.
Yeah.
What makes this additive so special?
Well, what's fascinating here is the difference it makes to how well a battery holds its charge over time, especially when it gets warm.
Oh, okay.
There's this one figure, 1.11, I think, in the text that essentially shows a graph where a battery with just a tiny bit of this lit-E-FOB keeps its oomph much longer when it's hot.
Keeps his oomph. I like that.
Yeah. Without it, a battery could lose like half its capacity in just a month and a half at 55 degrees C.
Wow, that's significant.
It really is.
Yeah.
This seemingly small additive tackles a fundamental challenge in battery longevity, especially in demanding environments like, say, EVs and hot climates.
Right.
It could potentially extend the lifespan of battery packs by years and, significantly reduce replacement costs for you.
Okay.
And furthermore, another figure, 1.12, indicates that lithium-ion also raises the temperature at which a crucial protective layer starts to break down.
The SEI layer.
Exactly, the solid electrolyte interface, the SEI. Think of it as a thin protective skin that forms on the anode, and it's actually vital for the battery's long-term health. LiFOP makes that skin tougher against heat.
So it's like giving the battery's vital components extra protection, especially when things heat up.
Mm-hmm.
The source also mentioned protecting against overcharging. That's something I definitely worry about with my devices.
Indeed. Yeah, in a battery pack with many individual cells, it's possible for one cell to become fully charged before the others.
Huh, right.
If charging continues, that cell can be damaged by overcharging. Redox shuttles are designed as a safety mechanism, kind of like a circuit breaker, to prevent this at the individual cell level.
Okay.
The challenge is that for common high-voltage battery materials like LiFOP, we need these redox shuttles to have an even higher activation point, a higher voltage before they kick in.
And that's where fluorine comes into the picture again, right?
Yeah.
I recall reading about highly fluorinated redox shuttles.
Precisely. The electron withdrawing nature of fluorine groups, this fundamental property of fluorine, is kind of the magic behind many of the advancements we're discussing. It acts like a tiny lever to fine-tune the electrochemical behavior of these materials, ultimately leading to more powerful and stable devices for you.
Okay.
So that property significantly increases the activation point, the redox potential of these shuttle molecules. This makes them suitable for protecting those higher voltage cathodes.
So connecting the dots, it's about enabling safer operation of more powerful batteries.
That's the bigger picture, yeah.
That makes perfect sense.
Yeah.
Now, another area where fluorinated materials seem to be making a big impact is in high voltage electrolytes, or HVEs. These sound like they could really allow us to push the boundaries of battery power.
They certainly show a lot of promise. The data presented in the text indicates that HVEs are much more stable and resistant to breakdown compared to conventional electrolytes like the standard Gen 2.
How much better are we talking?
Well, we're talking about efficiencies staying above 99.5%, even at 55 degrees C, whereas Gen 2 can drop below 98% at that temperature.
It doesn't sound like a huge jump, but I guess it adds up.
Oh, it adds up significantly over the many charge-discharge cycles a battery goes through in its lifetime. It means less wasted energy, longer life.
Wow, okay, that is a substantial improvement in efficiency. And the source even provided visual evidence, right? Electron microscope images of the cathodes after they've been used.
Yes, they did. Figure 1.27 provides really compelling visual evidence. After being cycled at 55 degrees C, the LNMO cathode using the conventional Gen 2 electrolyte shows this significant coating. Looks like gunk, really.
Okay, indicating breakdown.
Yeah, indicating the electrolyte is breaking down. But in stark contrast, the cathode from the cell using the HVE looks remarkably clean, almost like new,
So the HVE creates a much cleaner interface.
visually confirming its stability against oxidation right there on the cathode surface. It's pretty clear.
Seeing is believing. But it sounds like finding the absolute perfect electrolyte is still, well, a complex challenge.
It really is. This raises an important point about the inherent complexity. The text highlights the difficulty of finding a single liquid, a single solvent, that can simultaneously do everything you want.
Like what?
Like dissolve a high concentration of the lithium salts. The key ingredient for conducting ions resist being broken down by the positively charged cathode, and also resist being broken down by the negatively charged anode. It's a very, very delicate balancing act.
Okay, so electrolytes are essential as the pathways for ions. Got it.
Yeah.
But what about the actual materials that store the energy, the cathode materials? Fluorine seems to be playing a role there too with these interesting fluorophosphates.
Definitely. What's fascinating here is how introducing fluorine into the structure of these cathode materials can fine-tune their properties.
So,
Well, consider the average voltage of lithium insertion cathodes. That's essentially a measure of how much energy the battery can deliver its punch. The inductive effect of fluorine, because it's so electronegative, so good at pulling electrons towards itself, can actually increase this average voltage.
so it's like a tiny atomic adjustment that can lead to a more powerful battery. Give me some specific examples from the source.
Sure. The text mentions several. For instance, just doping. Adding a bit of fluorine to LiFePO4, which is a common cathode material, improves its electrochemical performance.
Okay.
Then there's LiVePO4F, which has a layered structure, kind of like sheets. We also see a whole variety of LiMPO4F and Li2MPO4F compounds.
M is the metal ion.
Right, M is the metal ion, like iron, titanium, cobalt, nickel. And they have different crystal structures, different atomic arrangements, like face-shared, edge-shared, corner-shared arrangements. Each one influences how lithium ions can actually move within the material.
It's like a whole family of fluorinated compounds with slightly different characteristics. One that really caught my eye was Li2F4F. The source highlighted its easy 2D pathways for lithium ions.
Yeah, like highways.
And very little change in volume when lithium goes in and out. That sounds like a recipe for a battery that lasts a long time.
Exactly. A volume change of only 3.7% during lithium insertion and extraction is remarkably low.
Why is that good?
Because big volume changes cause stress and strain. They can crack the material over time. Low volume change helps maintain the structural integrity over many cycles, leading to better longevity.
Makes sense.
The source also points to NaF3V2PO4-2F3 as an interesting hybrid ion cathode, suggesting that these fluoride-based materials could also play a significant role in sodium-ion batteries, not just lithium.
Oh, interesting. Sodium instead of lithium.
Yeah. And let's not forget the layered structure, Li5MPO4-2F2 compounds, which can operate at a high voltage around 4 volts.
So fluorine isn't just an extra. It's being built right into the core of these battery materials. The source also discussed surface fluorination of existing materials like the Linus 0.5M1.504 spinel. Why take that approach, just coating the surface?
The main goal there is usually to enhance the material's stability at the surface, where it meets the electrolyte. This particular spinel material can suffer from manganese dissolving into the electrolyte, which leads to the battery losing its capacity over time. So think of surface fluorination as creating a protective outer layer, like a thin shield, that prevents this dissolution right at that critical interface.
And how is this surface fluorination done? The source mentioned treating it with F2 gas. It sounds pretty reactive.
It is reactive, yeah.
Yeah.
Exposing the spinel powder to F2 gas introduces fluorine onto its surface. Interestingly, X-ray analysis data XRD suggests that this process can slightly alter the crystal structure just in that surface region.
Does you?
It makes the peaks in the XRD data a bit less defined, a bit broader. Table 2.3 and figure 2.10 showed that.
Okay.
And another technique, XPS X-ray photoelectron spectroscopy, confirms the presence of fluorine on the surface in different chemical states. Meaning some fluorine atoms are interacting with lithium ions, sort of ionically bonded, and others are directly bonded to the transition metals like manganese and nickel. It even seems the fluorine diffuses a little bit into the particles, not just sitting right on top.
Fascinating. It's like giving the battery material a fluorinated suit of armor.
That's a good way to put it, yeah.
Now, shifting gears a bit, the source also explored fluoride-based conversion materials and solid electrolytes. These sound like more fundamental changes to how batteries are made.
Indeed. Fluoride-based conventional materials have the potential for very high energy storage density.
Higher than current ones.
Potentially,
Yeah.
yes. Because instead of just having ions moving in and out of a host structure like intercalation,
Right.
these materials undergo a more drastic chemical transformation, a conversion reaction, during charging and discharging, which can involve more electrons and store more energy per unit weight or volume.
Okay. And how do they make them stable?
Well, the text mentions various synthesis methods like high-energy ball milling, basically smashing powders together really hard, and solid-state chemistry routes to create tiny nanocomposites. Making things nano-sized often helps them tolerate the changes during conversion and improve stability over many cycles.
Gotcha. And solid electrolytes. That's the big dream of getting rid of the liquid electrolyte for safety, right? No more fires?
Precisely. Safety is a huge driver there. The source discusses doped strontium fluoride, SRF2, and calcium fluoride, CHAF2, single crystals, as example.
Doped, meaning they add something else?
Exactly. By intentionally adding small amounts of other fluoride compounds, like those containing lanthanum or gadolinium, what we call aliovalent dopants, because they have a different charge, we can significantly improve their ability to conduct fluoride ions.
Ah, so the doping creates pathways for the ions.
It creates defects, vacancies, that allow the ions to hop through the solid structure more easily. The text provides specific conductivity values and activation energies, highlighting how effective these dopants can be. And similarly, adding things like barium, strontium, or calcium fluorides to other fluoride materials like LaF3 and CF3, which have a different crystal structure called tisonite, also greatly enhances their conductivity up to a certain point called the percolation threshold.
It's like creating a solid highway for the ions to travel on. The source even mentioned a kind of unusual fluoride-transporting electrolyte made from ammonium bichloride and polyethylene glycol. That sounds quite innovative.
It is quite different, yeah. What's intriguing about this approach is how the polyethylene glycol, the PEG polymer, seems to complex with and stabilize the ammonium bifluoride.
Stabilize how?
It makes it much more resistant to heat. Figure 3.9 showed that the complex holds together at higher temperatures than the ammonium bifluoride alone.
Okay.
This mixture, dissolved in another liquid called acetonitrile, can then act as an electrolyte that actually moves fluoride ions, not lithium ions.
A fluoride-ion battery.
Potentially, yeah. While this is a very new and interesting idea, the text is also clear that more work is needed before such systems could be used in, say, commercial lithium batteries.
What needs improving?
Mainly the reaction rates, how fast things happen, and their long-term stability over many cycles. It's still pretty early days for that specific approach.
Definitely sounds like an area with a lot of future possibilities.
Yeah.
Still in the early stages. Now let's talk about some of the more unusual fluoride-containing compounds mentioned. Fluorohydrogenated anions and ionic liquids. What exactly are these, and how might they be useful for storing energy?
Okay, so fluorohydrogenate anions, which have this general formula, FHNF, are formed when fluoride ions react with hydrogen fluoride, HF.
HF, hydrofluoric acid, nasty stuff.
Can be, yes. Salts containing these anions, like sodium fluorohydrogenate, NaIFHF, and ammonium fluorohydrogenate, NH4FHF, already have some industrial uses.
Yeah.
The source then explores fluorohydrogenate ionic liquids. These are essentially salts made with these anions that are liquid at or near room temperature.
Salts that are liquid.
Yeah, think of table salt, sodium chloride, which melts at like 800 degrees C. Ionic liquids melt much, much slower, often below 100 C or even room temp.
Huh.
Their atomic structures can arrange themselves in different ways, forming layers or columns as illustrated in figure 5.5. And the presence of that HF unit in the anion is thought to weaken the electrical attractions between the positive H's and the negative anions in the liquid.
So they're like super liquidy salts. What potential advantages do they offer for batteries or other energy storage devices?
Well, they can have reasonably wide electrochemical windows.
Meaning they don't break down easily at high or low voltages.
Exactly, which is a key requirement for high-energy batteries or capacitors. For example, the text mentions one called C2C1FH2.3F.
Catchy name.
Haha, yeah, typical ionic liquid nomenclature. But interestingly, by changing the positive ion in the liquid using different organic cations like alkylpyrrolidinium, phosphonium, or sulfonium, this voltage window can be further increased, made even wider.
So more design flexibility.
Right. The source also discusses fluorohydrogenate ionic plastic crystals. These are kind of a weird state of matter, solid-like, but with high ion mobility.
Oh,
They can have high ionic conductivities similar to the liquid ionic liquids, as shown in Figure 5.11. Their potential as solid-state electrolytes, maybe in electrochemical capacitors, has been investigated, offering potential safety benefits by preventing leaks compared to liquids.
the electrochemical capacitor. So fluorine is showing up in all sorts of energy storage technologies, not just batteries.
It really is versatile.
Speaking of components beyond the main electrodes and electrolytes, the source also discussed fluorine-containing binders and additives. PVDF is one I've definitely heard of.
Polyvinylidene fluoride, or PVDF, yeah, it's indeed a very common binder used in lithium-ion battery electrodes. It's kind of the workhorse.
Why is it so popular?
Its stability. It holds up really well in the harsh electrochemical environment inside the battery, plus it has good resistance to heat and chemicals. It basically acts as the glue holding the active electrode materials and conductive additives together and sticking them to the current collector foil.
Okay.
The source mentions that PVDF can exist in different crystalline forms, alpha, beta, gamma, delta, and that adding other small molecules, monomers, can sometimes make it more flexible and improve its ability to stick its adhesion.
Purity matters too.
Yes, the importance of using pure PVDF without any extra processing additives or ionic impurities that could cause side reactions is also emphasized.
So it's like the glue that holds the battery together, and fluorine helps it withstand the tough conditions inside. What about additives like FEC? I recall that being mentioned for sodium-ion batteries.
Yes, fluorinated ethylene carbonate, or FEC. It's proving to be a very effective additive to the electrolyte, especially for improving that protective SEI layer we talked about earlier. It's particularly helpful in sodium-ion batteries, but also for tricky electrodes like lithium metal and silicon-based anodes in lithium-ion systems.
Okay, so how does it help in sodium batteries?
In sodium-ion batteries, one of the figures, 16.5, shows that adding FEC causes an extra little electrochemical step during the first charge or discharge cycle.
A voltage plateau.
Yeah, an additional voltage plateau, which corresponds to the FEC decomposing preferentially to form a better, more stable SEI layer. And figure 16.6 demonstrates that FEC can significantly improve the reversibility, how well sodium ions can be repeatedly put in and taken out of the electrode, even in electrolytes that might otherwise decompose easily in sodium cells.
That sounds crucial.
It is. The source also touches on an interesting interaction, how the PVDF binder itself can sometimes react with sodium in NIBs, leading to defluorination, losing fluorine, and forming sodium fluoride.
That sounds bad.
It can be detrimental, yeah. But FEC seems to help mitigate this damage to the binder as well, possibly by forming its protective layer first. Figure 16.10 hinted at that.
It sounds like FEC is a really crucial ingredient for making sodium-ion batteries more stable and longer lasting.
It's certainly a very important additive being studied, yes.
Now let's move on to a completely different application.
Yeah.
Fuel cells. Fluorinated materials, particularly naphthalene, seem to be key players there.
Absolutely. Polymer electrolyte membranes, or PMs, are essential components in many types of fuel cells, particularly PE fuel cells, PEMFCs. And fluoropolymers, especially the perfluorinated sulfonic acid, or PFSA type, are the go-to materials because of their exceptional chemical and thermal stability. Naphthalene is the classic, most well-known example developed by DuPont.
Right.
The source briefly mentions other types of fuel cells like solid oxide or molten carbonate, but really focuses on PEMFCs because these fluorinated membranes are so central to how they work.
And naphthalene is well known for its ability to conduct protons, right? Hydrogen ions.
Oh.
Especially when it's wet.
Exactly. When it's fully saturated with water, typically at lower temperatures like 80 degrees C or below, naphthalene exhibits high proton conductivity, around 0.1 Siemens per centimeter. which is quite good.
But less good when it dries out at high temps.
That's the catch. Its performance can decrease significantly at higher temperatures, say above 100 C, as the water needed for proton transport evaporates. This is why there's a big drive towards high-temperature PEMFCs or HTPEMFCs, operating maybe 120 to 180 C.
What are the advantages of running hotter?
Several things. They're less sensitive to carbon monoxide impurities in the hydrogen fuel, which poison the platinum catalyst at lower temps. Reaction kinetics are faster, and managing the waste heat is often simpler.
Makes sense.
Figure 14.8 in the text shows the general chemical structure of nepheine and lists some of its key properties, like its equivalent weight and thickness. It also mentions that dissolving this PFSA material, the ionomer, and mixing it into the catalyst layers helps improve how effectively the expensive platinum catalyst is used.
So fluorine is essential for enabling efficient and durable fuel cells.
Yeah.
But the source also noted challenges, right? Like methanol passing through the membrane in direct methanol fuel cells, DMFCs, when using naphthalene.
That's a significant challenge for DMFCs, yes. Methanol fuel can easily diffuse or cross over through the naphthalene membrane from the anode side to the cathode side.
Why is that bad?
It leads to wasted fuel. It lowers the voltage produced by the cell because the methanol reacts directly with oxygen on the wrong side, and it often requires using more catalyst. While water is necessary for the fuel reaction in DMFCs, this methanol crossover issue remains a key area of research, trying to find membranes that block methanol better but still conduct protons well.
Okay.
The text also briefly touches on the ongoing efforts to understand and mitigate how these membranes degrade over time and to improve the overall durability and lifespan of PEMFCs, which is obviously crucial for them to be commercially successful and widely adopted.
It sounds like while fluorinated membranes are a cornerstone of fuel cell technology, there's still progress to be made.
Definitely still active research and development.
Finally, the last application the source explored was fluorinated carbon in supercapacitors. This was described as being less explored than its use in batteries.
That's correct.
Yeah.
While carbon materials, especially things like carbon nanotubes, CNTs, are excellent materials for supercapacitor electrodes
Why are they good?
because they have high mechanical strength, great electrical conductivity, and potentially very large surface area to store charge electrostatically.
Okay.
The effect of adding fluorine to them or using fluorinated carbons for supercapacitors is still being actively investigated and is maybe less mature than the battery applications we discussed. Figure 15.6 showed some detailed electron microscope images of fluorinated single-walled carbon nanotubes.
So what happens when you introduce fluorine to these carbon-based supercapacitor materials? Does it help? Hurt?
It's complex. Fluorination definitely alters the properties of CNTs and other carbon materials, things like their conductivity, surface properties, wettability by the electrolyte. The source looks specifically at porous carbons that are created by actually removing some of the fluorine from PTFE, polytetrafluoroethylene, Teflon, basically.
So starting with a fluorinated plastic and making carbon from it.
Yeah, through a defluorination process. These resulting carbon materials can have very large surface areas and a good amount of medium-sized pores, mesopores. Figures 17.7 and 17.4 showed data related to this.
And why are high surface area and pores good for supercaps?
Because supercapacitors store charge primarily by ions adsorbing onto the electrode surface. More surface area means more places for ions to adsorb, potentially leading to higher capacitance, more stored charge.
Interesting. So by starting with a fluorinated material like PTFE and then partially defluorinating it, you can create a highly porous carbon structure that's good for energy storage in a supercapacitor. It's almost the opposite of how fluorine is used sometimes in batteries and fuel cells, where stability is key.
Precisely. It really highlights how versatile fluorine chemistry is in tailoring materials for different ways of storing and converting energy. Sometimes you want the fluorine there for stability, sometimes you use it as a precursor to create a useful structure.
Well, this has truly been a deep dive into the fascinating world of advanced fluoride-based materials. It's amazing to see how this one element, fluorine, can be so vital in so many different energy conversion and storage technologies.
Indeed. From, boosting the performance and safety of our current lithium-ion batteries to enabling the development of next-generation technologies like solid-state electrolytes and more efficient fuel cells, fluorinated materials are clearly at the cutting edge of energy innovation.
Yeah.
They're contributing to higher energy storage, longer lifespans, improved safety, really across the board.
And it's clear that research is still very active, constantly pushing the limits of what these materials can achieve. It makes you wonder which specific fluoride-based material or application will ultimately have the biggest impact on how we power our future?
It's hard to say for sure. There's potential in so many areas.
Maybe you, our listener, have a clearer idea now, armed with this new knowledge. Perhaps this has sparked your curiosity to explore some of the research mentioned in our source or delve into related topics on your own. Thanks for joining us on this deep dive.